So chemical equations are the centerpiece of the study of chemistry. Chemical equations are a recipe that shows how reactants combine into new substances called products. So what you see there is a chemical equation. The left side are called the reactants. That's what you're putting into the chemical equation. And the right side of the arrow is called the products. That's what you're getting out. The one-way arrow indicates that the reaction moves from left to right. So here are three ways to interpret this equation. One molecule of CH4 and two molecules of oxygen, O2, combine to produce one molecule of CO2 and two molecules of water. So you can just think of it on a molecular basis. But we don't deal with molecules. We deal with these big bundles called moles that you've been introduced to. So 1 mole of CH4, so you see it's a big basket of methane molecules, and 2 moles of O2 combine to produce 1 mole of CO2 and 2 moles of H2O. So that's the second way we could think of it. The problem with this is if you have to have exactly 2 moles of oxygen and exactly 1 mole of CH4, then it's not really a very practical equation, because the chances you'll have exactly that many is pretty slim. So the real way we want to think of this is as ratios. So we can view this in terms of ratios. So whatever number of moles of CH4 reacts, twice as many moles of O2 react. This requires a ratio of 2 moles of O2 for every 1 mole of CH4, whatever those numbers are, and they'll produce the same number of moles of CO2 as CH4, because see, the coefficients in front of them are both 1. And the same number of moles of H2O as O2, because the coefficients in front of those are 2. So in other words, if I have 50 moles of CH4, I'm going to need twice that many, 100 moles of O2. If I have 25 moles of CH4, I'm going to need twice that many, or 50 moles of O2. So that's, you think of it in terms of whatever number of moles, all it means is that you have to have twice as many moles of oxygen as you have moles of CH4. So a particulate diagram provides a simple picture of the motion of atoms in a chemical reaction. The way that chemical compounds break apart and recombine will be covered later in this course. Particulate diagrams show a beginning and final diagram of the reaction. It might also show an intermediate state of the reactants. So there you see the one CH4 molecule and 2 oxygens. So through processes we'll discuss later in the course, they break apart into individual atoms, and then because it allows them to go to a more favorable energy state, they recombine as carbon dioxide and 2 water molecules. Antoine Lavoisier, known as the father of chemistry, developed the idea of conservation of mass in the late 1700s. Conservation of mass means that the mass of the reactants before a chemical reaction must equal the mass of the products after the chemical reaction. It means that if you bulldozed and burned Hoover High School to the ground, the mass of the rubble and smoke would be exactly equal to the mass of the school before it was destroyed. This means that the number of atoms of each element in the products must equal the number of atoms of each element in the reactants. Okay, so what we must do to use a chemical equation is balance it. That means we have to have the same number of each type of atom. In this equation we have V, O, H, and Cl. You have to have the same number on the left side of the arrow as the right side of the arrow. Without balancing an equation, it's like giving you a recipe for cake that just says you need flour, sugar, butter, eggs, but it doesn't tell you how many. So we're going to see how many of each of these compounds we need and how much we're going to get out. So what you do is you take each of the elements. So vanadium, you have 2 V's on the left side, so you just write that as VV, and you have 5 oxygens, so you write that as 5 O's. Then you have H and Cl, you have 1 of each of those. Then on the right side of the arrow, you have 1 V, 1 O, and then 3 Cl's, 3 chloride atoms. So you're just breaking everything into atoms. And then you have water, H2O. So what we're going to do is you want to start by picking one of the elements and balancing it. What you want to stay away from is an element that appears more than once on the same side of the arrow. So if you look at oxygen on the right side, it appears in VOCl3 and in H2O. So save that for the end, okay? That one's a complicated one because it appears in two places. All right, so what we're going to start with here, we're going to start with V. So you have 2 on the left and 1 on the right. So we're going to add another box of the VOCl3. So now you have 2 V's on the left, 2 V's on the right. But you have to add everything else in that molecule, the oxygen and the 3 chlorines. But now the V's are in balance. So next we're going to balance the Cl's. You notice now we have 6 Cl's on the right side of the arrow and 1 on the left. So we're going to add 6 boxes on the left to balance the Cl's. So there's 1, 2, 3, 4, 5. So there's 6 total on the left side. So now the chlorines are in balance, 6 and 6. The vanadiums are still in balance. Now the hydrogens, we need to balance those. So you'll see that we have 6 hydrogens on the left side of the arrow and 2 over on the right side in the water molecule. So we need to add 2 more water molecules. So there we do that. So now we have 6 hydrogens on the left and 6 hydrogens on the right. And as it just so happened, we saved oxygen, the tricky one. We saved that for the end. So you notice that we now have 5 oxygens on the right of the arrow and 5 on the left. So everything's in balance. So what you do is you put coefficients. In balancing, you never change the subscripts, those little numbers that you see. You only change the coefficients. So how many boxes do we have of V2O5? We have 1. We have 6 of HCl. We have 2 of VOCl3. And we have 3 of H2O. So that's a balanced equation. If you count, you have the same number of hydrogens on the left and the right. 6 times 1 and 3 times 2 over on the right side. You have the same number of vanadiums, the same number of chlorines, and the same number of oxygens on both sides. So that's a balanced equation, and that's what you must have in order to use a chemical equation. It must be balanced. Okay, I'm going to show you another method. Okay, now we're going to use a different method that doesn't take quite as much space as the box method. Eventually, you kind of want to get to using this standard method. So you're simply counting atoms on each side. So if you look at the left, you have 2 V's, and on the right, you have 1 V. On the left, you have 5 O, and on the right, you have 1 in the VOCl3 and another in the water, so that's 2 O total. On the left, you have 1 H. On the right, you have 2 H's, and on the left, you have 1 Cl, and on the right, you have 3 Cl. So we're going to go ahead and start balancing the V first. Now, you can't change the subscripts, the little numbers down below. All you can change is the coefficients, the numbers out in front. So we're going to go ahead and put a 2 up there. And that means we now have 2 vanadium on the right side. But it also, those coefficients, the 2, distributes through to the O and to the Cl3. So now how many O do we have on the right? We have 2 in the VOCl3 and 1 more in the hydrogen, or excuse me, in the water, H2O. So now we have 3 oxygens. And then what about the Cl3? Well, we have 3 of them originally, Cls, but now you have twice as many, so it's now 6. So now we have 6 Cl. All right, but the V's are in balance. Everything else is not yet. So next what we're going to do is we're going to do 6 hydrogens, or excuse me, 6 chlorines, because we have 6 on the right, chlorine, Cl. Now we need 6 on the left. So what we're going to do is we're going to change the 6 Cl to make 6 Cl on the left, and also 6 H. That 6 applies to the hydrogen and the chlorine. So now the Cl's are in balance and the V's are in balance. Okay. Next, we're going to go to the hydrogens, and we're going to put 3 water molecules. So that means we now have 3 times 2, or 6 hydrogens. But that also changed the number of oxygens over there in the water molecule. So now you have 2 oxygens in the VOCl3, and you have 3 in the H2O, so that's a total of 5. So now if you look at it, we have everything in balance. 2 V, 5 O's, 6 H's, and 6 Cl's. So those are the actual final coefficients up there above. So it's 1 V2O5 plus 6 HCl produces 2 VOCl3 and 3 H2O. That's the same coefficients we got from the box method as well. All right, so that takes care of how, what a chemical equation is and how you balance one.